Welcome back to our study of the fundamentals of operating systems. This course is based on the text Operating System Concepts 10th edition by Abraham Silberschatz, Greg Gackney, and Peter Galvin, published by Wiley Publishing. In our last lesson, we spent quite a bit of time discussing how processes are created and how some processes create other processes. We have a parent-child relationship going on. If you take a look at this graphic that we see here, you see the process at the top, System D. That is the root parent process for every process in Linux or Unix. These others are children of that root, and you recall that in that last discussion we found out that children of a process can either get their own resources from the operating system or they can be restricted to a subset of resources from the parent. Looking at this graphic here, I would assume that all these processes are getting their resources from the operating system. Why don't we pick up where we left off in that last lecture? A process terminates when it finishes executing its final statement and asks the operating system to delete it by using the exit system call. At this point, the process may return a status value, typically an integer, to its waiting parent process via the wait system call. All of the resources of the process, including physical and virtual memory, open files, input-output buffers, are deallocated and reclaimed by the operating system. You recall the operating system's responsibilities to allocate, monitor, and deallocate. So in this case, it's deallocating. Termination can occur in other circumstances as well. A process can cause the termination of another process via the appropriate system call. Usually, such a system call can be invoked only by the parent of the process that is to be terminated. Otherwise, a user or a rogue application could arbitrarily kill another user's processes. Note that a parent needs to know the identities of its children if it's to terminate them. So, when one process creates a new process, the identity of the newly created process is passed to the parent. A parent may terminate the execution of one of its children for a variety of reasons, such as these. The child has exceeded its usage of some resources that has been allocated. To determine whether this has occurred, the parent must have a mechanism to inspect the state of the children. Reason number 2 is that the task assigned to the child is no longer required. Or finally, the parent is exiting, and the operating system does not allow a child to continue if its parent terminates. Some systems do not allow a child to exist if the parent has terminated. In such systems, if a process terminates either normally or abnormally, then all of its children must also be terminated. This phenomenon, referred to as cascading termination, is normally initiated by the operating system. When a process terminates, its resources are deallocated by the operating system, as we've already said. However, a child's entry in the process table must remain there until the parent calls wait, because the process table contains the process's exit status. A process that's been terminated and whose parent has not yet called wait is known as a zombie process. All processes transition to this state when they terminate, but generally they exist as zombies only briefly. Once the parent calls wait, the process identifier of the zombie process and its entry in the process table are released. Because of resource constraints such as limited memory, mobile operating systems may have to terminate existing processes to reclaim limited system resources. Many websites contain active content such as JavaScript, Flash, and HTML5 to provide a rich and dynamic web browsing experience. Unfortunately, these web applications may also contain software bugs which can result in sluggish response times and can even cause the web browser to crash. This isn't a big problem in a web browser that displays contents from only one website, but most contemporary web browsers provide tabbed browsing, which allows a single instance of a web browser application to open several websites at the same time, with each site in a separate tab. You and I have done that many times. To switch between the different sites, a user need only to click the appropriate tab. This arrangement is illustrated in the image at the bottom of the slide. A problem with this approach is that if a web application in any tab crashes, the entire process, including all the other tabs displaying additional websites, crash as well. Google's Chrome web browser was designed to address this issue by using a multi-process architecture. Chrome identifies three different types of processes: browsers, renderers, and plugins. The browser process is responsible for managing the user interface as well as disk and network I/O. A new browser process is created when Chrome is started. Renderer process contains logic for rendering web pages. Therefore, they contain the logic for handling HTML, JavaScript, images, and so on. As a general rule, a new renderer process is created for each website opened in a new tab, and so several renderer processes may be active at the same time. A plugin process is created for each type of plugin in use, such as Flash or QuickTime. Plugin processes contain the code for the plugin as well as additional code that enables the plugin to communicate with associated renderer processes and the browser process. The advantage of the multi-process approach is that websites run in isolation from one another. If one website crashes, only its renderer process is affected. All other processes remain unharmed. Furthermore, renderer processes run in a sandbox, which means that the access to the disk and network I/O is restricted, minimizing the effect of any security exploits. When I was a system administrator, I had one of my techies come to me one day complaining about Chrome because he kept seeing all these processes opening up, the renderer and the browser and the plugin process and so on, claiming that Chrome was using too many resources. Processes executing concurrently in the operating system may be either independent processes or cooperating processes. A process is independent if it does not share with any other processes executing in the system. A process is cooperating if it can affect or be affected by other processes executing in the system. Clearly, any process that shares data with other processes is a cooperating process. There are several reasons for providing an environment that allows process cooperation. For example, information sharing. Several applications need the same piece of information. For example, copying and pasting. We must provide an environment to allow concurrent access to such information. Also, computation speed up. If we want a task to run faster, we have to break it into subtasks, each of which will be executing in parallel with the others. Notice that such a speed up can be achieved only if the computer has multiple processing cores. And then, of course, there's modularity. We may want to construct the system in a modular fashion, dividing the system functions into separate processes or threads. Cooperating processes require an inter-process communication mechanism that will allow them to exchange data. There are two functional models of inter-process communication. One is shared memory, and the other is message passing. In the shared memory model, a region of memory that is shared by the cooperating processes is established. Processes can then exchange information by reading and writing data to the shared region. In the message passing model, communication takes place by means of messages exchanged between the cooperating processes. The two communication models are contrasted in this image. Both of the models just mentioned are common in operating systems, and many systems implement both. Message passing is useful for exchanging smaller amounts of data because no conflicts need to be avoided. Message passing is also easier than shared memory to implement in a distributed system, although there are systems that provide distributed shared memory. Shared memory can be faster than message passing, since message passing systems are typically implemented using system calls and therefore require the more time-consuming task of kernel intervention. In shared memory systems, system calls are required only to establish shared memory regions. Once the shared memory is established, all processes are treated as routine memory accesses and no assistance from the kernel is required. Inter-process communication using shared memory requires communicating jobs to establish a region of shared memory. Typically, a shared memory region resides in the address space of the process creating the shared memory segment. Other processes that wish to communicate using this shared memory must attach it to their memory space. Remember that normally the operating system tries to prevent one process from accessing another process's memory. Shared memory requires that this restriction be lifted for the two or more jobs that are sharing the space. They can then exchange information by reading and writing data in the shared areas. The form of the data and the location are determined by these processes and are not under the operating system's control. The process is also responsible for ensuring that they're not writing in the same location simultaneously, which is slightly different than our egg scenario, unless we have individual partitions in the bin for each egg. To illustrate this concept of cooperating processes, the authors consider the producer-consumer problem, which is a common paradigm for cooperating processes. A producer process produces information that is consumed by a consumer process. For example, the producer-consumer problem provides a useful metaphor for the client-server paradigm. We generally think of a server as a producer and a client as a consumer. For example, a web server produces web content such as HTML files and images, or perhaps even a database of stock market reports, which are consumed or read by the client web browser requesting the resource. Since this resource may be updated by the producer, and for that matter, maybe the consumer, it represents shared memory. Let me confuse you a little. When the user of the web browser is updating the database, he or she becomes the producer, and the web server becomes the consumer. When the web server is distributing the data, the web server is the producer, and now the web browser is the consumer. One solution to the producer-consumer problem uses shared memory. To allow the producer and consumer processes to run concurrently, we must have an available buffer of items that can be filled by the producer and emptied by the consumer. This buffer will reside in a region of memory that is shared by the producer and the consumer. A producer can produce one item while the consumer is consuming another item. The producer and consumer must be synchronized so that the consumer does not try to consume an item that has not yet been produced. Two types of buffers can be used. The unbounded buffer places no practical limit on the size of the buffer. The consumer may have to wait for new items, but the producer can always produce new items. And then there's the bounded buffer, which assumes a fixed buffer size. In this case, the consumer must wait if the buffer is empty, and the producer must wait if the buffer is full. The producers and consumers scheme requires that these processes share a region of memory and that the code for accessing and manipulating the shared memory can be written explicitly by the application programmer. In this lesson, we've completed our discussion of how processes can be created and how they can spawn other processes and the relationship between those processes and so on. We also started touching on how processes are able to communicate with one another. And we found that there are two classifications of communication. One is shared memory and the other is message passing. We concluded this lesson by going into some detail about how shared memory works. This is a good time for us to take a break and review our notes on this subject. And when we come back to our next lesson, we will start examining how message passing works for communication between processes in the operating system. So look over your notes, take care of any business you need to do, and when you're ready, come on back and we will continue.